Okay, hello everyone. As you know, we will continue the rest of the semester online remotely. So this is going to be the first lecture on video, the first of many. And I will just go back a little bit, go back to lectures and review a little bit section 7.3, orthogonal transformations and orthogonal matrices. I will just give you a 10-minute review to see basically how the technology works, and if you have any complaints about it, and then we'll go with the regular lectures in the coming sections. So let's just go back and see if we can basically review a little bit this idea of orthogonal transformations and orthogonal matrices. So let's just take a linear transformation T from R squared to R squared, such that it sends a vector a vector u with coordinates x1, x2 to another vector with coordinates x1, 2, x2. So it's obvious that the the matrix for this linear transformation is this matrix A, which happens to be a diagonal matrix with entries in the diagonal 1 and 2, right? And so let's just see what happens now to this elliptic shape. So we have an ellipse in the first R square, right? So we have this ellipse, and so if we actually try to draw some easy way to draw this ellipse is that it intersects the x-axis in the plus minus 1 point and the y-axis or x2 axis in the plus minus 2 points, right? So now if we see what happens to this ellipse under this transformation, x1 is replaced by x1 and x2 is replaced by 2x2, right? So 2x2 becomes 4x2 squared, and 4 is cancelled, so we get something like this, okay? So now this thing is now a circle. So the ellipse became a circle under this transformation. So what's the point of this example? So linear transformations change shapes. Okay, so under a linear transformation, the geometrical shape could actually change. So can we somehow characterize these linear transformations which preserve shapes? Well, in order for a linear transformation to preserve shapes, it has to actually preserve what? It has to preserve lengths. So a linear transformation, we will call it orthogonal if it preserves the length. So mainly initial vector x under the has the same magnitude as the image vector t of x. Okay, the corresponding matrix for such linear orthogonal maps or transformations will be called an orthogonal matrix. Now the name might look a little bit strange, or it doesn't make sense at the moment, but you'll see why we actually do that. Okay, so the first proposition that we proved in class was that orthogonal transformations preserve orthogonality. What does that mean? So if U is orthogonal to V, then the images of these two vectors TU and TV are also orthogonal to each other. And here is a proof using basically the idea that two vectors idea of this exercise 7.3. So two vectors are orthogonal if and only if they satisfy this Pythagorean relation, right? So the sum of the squares is equal to the square of the sum. Okay. So the next theorem that we proved was the following. So a linear transformation is, so there is something missing here, is the word orthogonal missing. So a linear transformation is orthogonal if and only if the image of the standard basis is an orthonormal basis. Okay, and now you will see that a characterization for the corresponding matrices of orthogonal maps. So a matrix is orthogonal if and only if its columns form an orthonormal basis. All right, so again, the proof of this is rather easy. So The next thing we proved, and this, again, I call them theorems mostly to bring them to your attention, but they are really easy exercises. The next result is that a square matrix A is orthogonal if and only if its inverse is actually the same as its transpose. And here you have a quick proof of that. Okay, so the proposition 7.2, it's an easy exercise. It says that not only the property of being orthogonal is preserved, but actually the inner product of any two vectors is the same as the inner product of the corresponding images when we have a matrix, a linear transformation, orthogonal transformation from Rn to Rn. Okay, so theorem 7.6, it reviews and it gives you basically a nice list of equivalent conditions when matrix is orthogonal. So basically the transformation has to preserve length. There is no n here, so get rid of that. Preserve lengths. Okay, the columns of A form an orthonormal basis. Yes. AT times A is the identity. In other words, the inverse of A is AT, the A transpose, and A preserves the inner product. In other words, UV is equal to AU AV. Yes? Anyway, this proposition 7.3 is really what was a nice lemma with properties of the transposes in chapter 2. Yes, so basically just to review basically some of the basic transposes, basic properties of the transpose. Okay, so let's just stop the first test of these videos here, and we will continue with a review of what is left in the next video. Thank you very much.